Hello everyone. Now we talk about probability. I skip statistic. It's because statistic is just about many definition, and I mean my English is not good to explain many definition. I mean, we can just learn with our teacher about statistic. It's I mean, the the hardest thing is just remember the definition, and for the calculate it's really easy because it's just related to plus, minus, time, and divided by. So it's not a big deal. So let's talk about probability, which is really interesting. Really interesting. Why? If you know probability, you can go to Macau and gamble. Yes, gamble. It's really good. You can earn many money in Macau. I don't know why it's still allowed. Gamble is still allowed in Macau, but not allowed in mainland of China. Oh my god, interesting. So let's continue. Why the two looks really different? No worries. Okay, introduction to probability. Okay. If you roll a standard fair dice, there are six possible equally likely outcomes: 1, 2, 3, 4, 5, and 6, each having probability 1/6 of occurring. So I mean, you might be interested. A combination of outcome is known as an event. The probability of an event we can write as PA. Yes, probability of an event A, PA. Yeah, it makes sense. And you might wish to repeat the roll of the dice several times. Each repetition of the process is known as a trial. And also one way of estimating the probability of an event is to use the relative frequency. So definition is really important. Now I just wanna find some example to explain. So yeah, I mean actually the basic method of probability is use the number of the outcomes, the number of the event, the thing you want, over all the possible outcomes. What I mean, for example, 1, 2, 3, 4, 5, 6. For example, first time, I want a odd number 1, 3, 5. So in six different we have 6 possible outcomes, and they are equally. And the outcomes I want is 1, 3, 5, which have three outcomes I need. So the number of outcomes I need is 3. All the possible outcomes is 6. So I use 3/6, which is equal 1/2. So it is basic method. So here we have 80 collectible card packets, and 23 were found to contain a special rare card. So we have 80 possible outcomes, and only 23 outcomes we need, and everything is equally likely. So P pack contains rare card is 23 over 80, right? It makes sense, right? So yes, the thing is, if all outcomes are equally likely, then PA is equal NA over NU. U is all the possible events. So number of all the possible events. So it's the thing I want to explain. And a fair standard 6-sided dice is rolled. Find the probability that the outcome is a prime number. Remember the definition of prime number. Don't forget it. Prime number is a positive integer which is more than 1. And also this positive integer only have 2 factor, which is 1 and itself. Okay, remember, we don't discuss 1. We don't discuss whatever 1 is prime number or not. Remember, because the definition of prime number is all the is if this positive integer is more than 1 and only have 2 factor which is 1 and itself, then it's prime number. So 235 is prime number. So we have three outcomes we need in event A, and in total we have 6 possible outcomes, and all the outcomes are equally likely. So P prime is 3/6, which is equal half. And also for this, complementary event, it's also easy to explain. I mean, if a dice, if the probability if the probability that the outcome is a prime number is 1/2, then the probability that the outcome is not a prime number will be also 1/2. Why? This 1/2 is because of 1 minus 1/2 is equal 1/2. Because in a whole set, if those group is prime number, and the thing other stuff, obviously they are not prime number. It's like if you are not man, then you are women. Okay, this gender is in like science, not mental. It's physical gender, not mental gender. So okay, let's skip about this topic. So the probability of the complement of the event A will be 1 minus the probability of event A. Yeah, so for example, the probability of no buses arriving in a 10 minutes interval is 0.4. So the probability of at least one bus arriving in that 10 minute interval will be 1 minus 0.4, right? So expected number of occurrence. Oh my god. So, I mean, this thing is just used for oh my god, I'm not sure the word. Yeah, I mean, this thing is just used for. Oh my god, I know how to say it in German and Chinese, but now I don't know how to say it in English. Assess. I mean, this formula is just used for predict. For example, if you roll 120 times of dice, I mean, I think you guys will think for each number it will be 20, 20, 20, 20, 20, 20 equally. But I mean, in the real life, it cannot be exactly equally, but the number will not really far from 1/6. So this formula is how to calculate the expected number of occurrence. So A will equal probability of event A times the n, where n is a number of trails. So for example, here's an example. So I mean, if we use dice to dice this example. So for example, if we roll 120 times dice, the expect number of occurrence of if the outcome is prime number, how much is it? Yes. So we know that the probability of prime number when we roll dice, it will be 1 over 2. 1 over 2, and we roll 120 times. So we use 120, which is the number of trails, time 1 over 2, which is the probability of event prime number. So the result will be 60. So in ideal condition, if we roll 120 times of dice, we will get 60 times if the outcome, we'll get 60 times the outcome is prime number. Oh my god, why I have so many grammar mistakes? So never mind. Oh, let's go. So I mean, sometimes if you are worried or you're not sure of something, because sometimes you have two events in a question, and these two events sometimes they have some area. For example, this case. In a school year of 60 students, 32 study geography and 40 study biology. And also, I mean, the thing is, if 18 study both of these subjects, yes, the thing is, remember here's a point that people always make mistake. 32 students study geography. Do they tell you that it means only 32 students only study geography? So it's different. 32 students study geography and 32 students only study geography. It's different. So in this case, if 32 students study geography, it means some students maybe also study biology. And in this case, we know that 18 students study both of this subject. Here will be 18. And 32 students study geography. It means here's in total 32 students study geography, no matter if he study biology. So in Venn diagrams, this area we will mark 18. This area will be 32. The whole B will be 32. So obviously this area will be 14. And this area we use same method. This area it will be 22. Oh my god. B is biology, G is geography. Oh my god. I thought geography is left side, biology is right side. No, never mind. So here will be 22, here will be 14. And because in total we have 60 students, actually also remember that sometimes it's possible that here some student learn neither biology nor geography. So just check. 22 plus 18 plus 14, how much is it? It's 54. It means here 6 students learn nothing. So those areas, the left area, we've marked 6. So if you calculate the probability of a randomly select student studying neither geography nor biology will be 6 over 60, which is 0.1. Oh my god, my stomach. Venn diagram is help you to summarize or make the data obviously, and here's another diagrams also can help you to calculate the probability. Tree diagrams is always used for some case like tell me the probability if if I roll 3 times dice, the result is always is all 6. So it's like it means I'm really lucky when I roll three time dice and the outcome is always 6. So we can draw a graph like that. So we have 56% to get not 6, and 1/6 per 1/6 we can get 6. And if first time we cannot get 6, it means no matter the second time is 6, we cannot achieve my requirement. So here's all. So we only discuss if first time is 6. We still have 5/6 probability that we cannot get 6. The result is not 6, and 1/6 we can get 6. And the thing we do is continue. So how can we calculate how the probability that we can get 3 times 6? So it will be 1/6 times 1/6 times 1/6, because the condition of we roll second dice is that the first time we get 6. So we have 1/6, the problem like 1/6 that we can get 6. Then we roll again. We still only have 1/6 that we can get 6. Then continue. So the probability that if I can get 3, 6, it will be 1/6. The cube of 1/6, which is, oh my god, okay, I will use a really formal, correct English to, yes, I will just read it here. These are used when you have one event followed by another, particularly when the second event depends on the first. Oh my god, this is the word I need. The second event depends on the first. Then we can use tree diagrams. And remember, if here's something like second event depends on the first event, the event base depends on the event before, then when we calculate it, we need time. That's why I use time here. 1/6 times 1/6 1 time 1/6, which is 1/6 cube. Because for the probability of event depends on another event, we use time to calculate. So here's the example. Time together get the probability of this event. Time together, time together, time together. Yes. So it also can help you because for this case, if it is not raining, then the probability of Anya traveling by car is 1/2. Find the overall probability of Anya traveling by car. So C is car. C is without car. So I mean, this tree diagram also can make all the information obviously. Then we just calculate, because R or not rain or not rain is no matter the probability we calculate, we only care about if C here is C, not C, not if we only care about if it is C or not C. So we just care about C. So rain with car, 1/6. Not rain, still with car, 3/8. 1/6 plus 3/8, then we can get 13/24. Also, I mean, here's another method. Here's third method, sample space diagram. I mean, actually, sample space diagram and the tree diagram is similar if we only have 2 events. But I mean, if we have 2 events, then sample space diagrams will be better. But because imagine that. Okay, four side dice. Right? 1, 2, 3. Imagine that 1, 2, 3, 4. we have 4 outcome at the first time, and the second dice, for each number we have to draw this four branch again. It's really slow, but I mean for this case, simple space diagrams will be easier, isn't it? Yes, and we have so many. The result we get will be here. So all the things we needed will be here. Because for this case, we have to draw 20 branch, but for this case, we only need a chart. So if we have 2 event, sample space diagrams will be easier, no matter it's a depend event or not. Because actually, this side, they said it's row 2 fair standard 4-side dice are row 2 fair standard 4-side dice. But actually, if you roll 2 fair standard 4-side dice, it's same as if you roll a dice 4-side dice 2 times. So it means same thing. So doesn't matter. You can use tree diagrams and also use sample space diagram, but the result should be same if you don't make calculating mistake. So for example, roll dice, the sum is larger than 6. Then yeah, we list all the outcomes, and we know in total we have 16 possible outcomes, and only 3 outcome is follow the condition. Sum is larger than 6, so 3 over 16. Table outcomes. Oh my god, table outcomes is same as seen here. I mean, it's use same method, fiction, non-fiction. I mean, because for probability, the outcome for only for one event, it can be anything. It can be maybe related to number, related to letter, related to some real event. For example, in this case, fiction, non-fiction. Number of the pages, here's 3 range. And yes, we just put all the data. The number of page which is more than 0, less than 200, and also a fiction. It is a fiction. So we know that here's 23 fictions which have less than 200 pages. And the tables, why we need these tables is because maybe they will ask you the probability that you get the book which has less than 200 pages. Sometimes they will not care about if it's fiction or non-fiction. They only care about how many pages do they have. Or sometimes they will only care about the probability if you get a fiction or you get non-fiction. They will not care about pages. So this chart is also helpful. Yes. Oh, here's something. Combine event. Okay, I will just read something here. If you want the probability of either event A or event B occurring or both occurring, then you can think of this from a Venn diagram as being the probability of being in the union of these 2 sets, A union B. Simply adding the probability of being in A to the probability of being in B will count the intersection twice, so you need to then subtract 1 lot of the intersection. So the probability of combination of A and B is equal probability of event A plus probability of event B minus the probability of the intersection of A and B. It's a really interesting. It's really interesting, but I can just use this graph to explain it. What is A combine B? It is the whole thing with the color. And A is this one, B is this one. A plus B is equal this shape plus 2 times of this shape. What is this small shape? It is the intersection of A and B. So that's the reason that combination of A and B is equal A plus B minus the intersection of A and B. I mean, for the probability, is same. Now we just use the formula to calculate. If we know PA is 0.4, PB is 0.3, and the PA union B is 0.5, then find the probability of intersection of A and B. So we just use. So we know that 0.5 is equal 0.4 plus 0.3 minus this thing. Then move the probability. The PA intersect B will be 0.2. Also, here's something. If A intersect B is equal to 0, or equivalently PA union B is equal to PA plus PB, then it means event A and B are mutually exclusive. What does that mean? So actually, if we use the Venn diagrams, it's obviously the graph will look something like that. For example, if you're a man, you cannot be women. And you cannot be woman. If you're a woman, you cannot be a man. Also, you can be LGBTQ. But event that you are man and the event that you are a woman, they are mutually exclusive events. So here's, mutually exclusive events. If you want to check if these two events are mutually exclusive, then you just prove PA intersect B is equal to 0, or A union B is equal to PA plus PB. On the condition of probability, maybe use this graph will be better. So the probability of event A actually is 0.5. Oh my god, I make a mistake. The probability that the probability of event A is 0.4. The probability of event B is 0.5. Wait, I will draw it again. The probability of event A will be 0.4. The probability of event B will be 0.5. Therefore, if we want to know that the probability, oh my god, I will really make an example, like the textbook. The probability that you select the selected student study French is 0.4, and the probability of select student study Spanish is 0.5. Then maybe you want to know that what is the probability that if I select a student who studies Spanish also study French, then we just use, because we know that here's 0.5 probability that he learns Spanish, and the probability he learn both French and Spanish is 0.1. So the probability that if you select a student from Spanish who studies Spanish, also study French is 1/5. Why is work? Because it is a condition. Listen. What is the probability that if I select a student who studies Spanish, he also study French? The condition is he studies Spanish. The thing I ask is he also study French. So that's the reason. So if we use like common formula, it will be something like that. If the probability of event A happening is dependent on the previous event B, then the probability is said to be conditional. This can be written as this. So the formula of this will be intersection of two events over the condition event. Yes, you see, the previous event B is right after. The event happening is the event we want to calculate. The first event is before the line. Yeah, oh my god. So it is a formula. And what is independent event? Two events are independent if one doesn't affect another. In other words, if P. Oh my god. Substituting this into the above formula and rearranging gives the following convenient relationship of independent events. So, I mean, if we know that these two events are independent, then we have this formula. And the definition of independent events is this. Actually, how to explain it? They are independent. Oh my god. Oh my god. It's not something really complex. Independent events, it means no matter what happened about first event A, the result of event B is still following the probability. So it's fine. So I mean, if these two events is not related, then we have an easy way to calculate the probability of insect events. Oh my god. Oh my god, how can I explain it? Oh, for example, I mean, I don't know if you guys met this question before. It's like, if I roll a dice and roll a coin, the probability that if I get 6 and nail, tail. Oh my god, flower or number. Oh my god, I just use flower and number. So I mean, no matter what you get, you get which number in dice, the probability that you get a 1 is you get the number in coin is still 1/2. So these two events are independent. So when you calculate the probability of get number 1 in dice, and the probability that you get flower in coin is equal to 1/6 times 1/2. So the result of get 1 and flower will be 1/12. So it's something like that. The probability of a randomly chose individual in a society being male is 0.52. The probability of individual being an Irish origin is 0.18. These two events is not related, obviously. No, it's not obviously, but if these two characteristics are independent, here's a condition. I mean, sometimes if you want to use this formula, maybe they will tell you these two characteristics are independent, but sometimes you have to prove they are independent. So it is the point. It's all the thing about probability. For the probability, you have to think a lot, like some logic, especially like about independent events, mutually exclusive events. This two thing is really interesting because this two thing is also similar to combination, similar to the combination, something like that. It's related to higher level first chapter. So I mean, when you learn about probability, just think a lot and maybe play some real example. I mean, if you want to improve your probability by at least two die and by one poker and keep some coin, play more and just feel about probability, then it can help you to understand. So bye.